Let's look at a surface integral. The surface integrals are analogous to the line integrals for the scalar function and also the vector valued function. So we'll see a lot of similarities with these calculations. So this surface is given in terms of Cartesian coordinates. We have z equal 11 minus 6x plus 8y, and then x runs from 0 to 1 and y runs from 0 to 1. Now, when we have the surface described in the Cartesian coordinates, we simply parameterize by the graph. And so the parameterization for the surface will look like this: x comma y comma the z, where we replace z with this expression. Now, again, a very simple formula will be relied upon to compute the surface normal. And we always are looking for the outward normal, especially when we start to study Stokes' theorem and Gauss's theorem. And so this also admits to a very simple formula. If you just take the cross product of the x partial of r with the y partial of r, you get a very simple formula here. The negative of z differentiated with respect to x, the negative z differentiated with respect to y, and 1. Sometimes I just say negative zx, negative zy, comma 1. And that's real simple to remember. Also, with the Cartesian representation, you can think of determining this via a gradient. So you have many ways to compute this, but since this will cover all the possibilities, it's probably good to remember what I have in the red box here. And so you can easily look at the expression for the surface, and we get the negative of zx to be negative 6, the negative of zy to be 8, and then of course the 1. And now, since we're actually going to do the surface integral of a scalar valued function, we need the norm of the normal. And so that's easy to compute. So we have negative 6 squared plus 8 squared plus 1 squared, which will give us the square root of 101. So this is completely analogous to the line integral. And so now the notation for the surface integral, very simple. We have the double integral over the surface of the function f of xy comma z integrated with respect to the surface. Now, again, just like with the line integrals, we will have a curve around which we're computing the line integral, and here we'll have a ds where the s is lowercase. So very similar to what we've been used to. So now what we want to do is go ahead and substitute for z. That is 11 minus 6x plus 8y, and then of course we have the norm of the normal, which we have here, and then the area computation. Now, of course, this is the area element. You could write this as dA or dx dy. We're still being fairly informal here because we haven't really attached an order to this, and if that bothers you, you can just go ahead and write dA. But this is very straightforward. So now we just combine like terms. We'll get a negative 5x plus 3y plus 11 dx dy. And of course we factor the square root of 101. And now we integrate with respect to x. This order is fine. And then we get negative 5 halves x squared plus 3xy plus 11x. That is integrating all of these terms with respect to x. And of course the lower limit zeroes out everything. So we're just left with a negative 5 halves plus an 11 plus a 3y. Now, what I've gone ahead and done here is I just write the 11 as 22 over 2 to get a common denominator. So we have the square root of 101 of the integral of 0 to 1 of 17 halves plus 3y integrated with respect to y. Again, very straightforward. So now we have square root of 101, 17 over 2, y, 3 halves y squared. And again, the lower limit zeroes out our antiderivative. We only have the 1 that survives. So this nicely gives us a good number. We have 17 halves plus 3 halves, which is 20 halves, which is 10. So our final answer will be 10 times the square root of 101. Like I said before, take the opportunity to compare the similarities between the line integral of a scalar function and the surface integral of a scalar function. I think you'll find them to be very much alike and make this process very simple. And we are done.